Good morning, and thank you all for coming. I offer my sincere apologies to those who can't quite get in the door, and one way or the other will make the content available to you. At Facebook, we do a lot of different things. Just last year, Mark Zuckerberg rolled out our 10-year roadmap. And 10 years in tech is a very long time, so you can see the long-term bets. Virtual reality, AI, and this other one, connectivity. It's not immediately obvious what that is, but I'm going to talk about that today. That's where I live. The goal is to get internet in some form or another to the whole world. Right now, fewer than half of the people in the world are well connected to the internet, and so we'd like to change that. So this leads to some pretty fun data science problems. If you want to get internet to people, you need to know where they are, who's connected and who's not, and then after you identify the unconnected people, to be able to figure out how best to connect them. This is the part that I'm focusing on right now. If we're looking at a small region like this neighborhood, it's not a big deal for an individual to sit down and figure out where the likely locations are for where people live and where they work. But as that scales up to a city or to a state or a nation or a continent, it becomes impractical to do that by hand. And so the downside is you have to automate to make that happen. The upside, if you like playing with algorithms, this is an excuse. There is no argument that there's a cheaper way to do this. You have to automate it. And so you get an excuse to dive into your tool set and make some new ones. Now, we already know approximately where people live in the world. Almost all governments do some kind of census and break up the world by census tracts. But if you zoom in a little bit, for instance, look at some of the regions in Saudi Arabia, those are very large, many thousands of square kilometers. It's not good enough to know an average population density. We need to know exactly where people are to know how best to connect them. This is what we need. This is a small village in India, and what we'd like to know is how those houses are distributed. So if you look at the plot over on the right, each of those little white dots represents one of the houses. And if you look, for instance, out along some of those small roads, you can identify very small houses on the left and see that there, sure enough, is a white dot that corresponds to that on the right. With this level of granularity, now we can start making really useful decisions. Similarly, you can see how in a farming community in Kenya, where those houses are distributed a lot more evenly, you can look at the dots on the right that correspond to those houses. This suggests a very different connection technology. And yet another, here's a village in Mozambique that appears to have sprung up organically around the intersection of two major roads in the countryside. The houses are 1 or 2 layers deep, all lining those roads. This suggests yet another connection technology. So the way we do this is with neural networks. And we've got to hear a lot in the talks about deep neural networks and deep learning. There was a fantastic talk yesterday about how neural networks work. I'm going to do another explanation of how neural networks work that actually, if you attended, there's a lot of overlap, but it's a different take. That makes me excited because as someone who's played with these algorithms, to really get them to behave well and to get what you need out of them, you kind of have to understand how they work. You think of it like driving a car. Most cars you can get in, turn the key, get from point A to point B. But if you're driving a Formula One racer, you need to know exactly what's going on under the hood in order to get the most performance out of it. When we're working at a global scale, we can't afford the off-the-shelf generic settings on some of these algorithms to be able to get robust and fast enough results. If you already know how neural networks work, I've hidden a couple of Easter eggs in here for you. There are 2 errors. One is trivial and one is substantial. So if you can find it, I'll ask after the talk. So let's start with a very simple toy problem. We have a 4-pixel camera, not 4 megapixels, but just 4 pixels, and we'd like to be able to identify different types of images. So all solid, so like all light or all dark, vertical lines, diagonal lines, or horizontal lines. Now the trick to doing this is we can't just write simple rules for which pixel is light and which is dark, because both of these images are horizontal lines, but no pixel has the same value in these two images. So we have to do something a little smarter. So we have a good excuse to try a neural network. The way that we would approach this is you take all of your inputs, in this case each of your pixels, you break it out into its own input neuron, which is just a placeholder that you assign a number to. In our case, we'll assign dark pixels a -1, light pixels a +1, and then we can convert that image to a list of numbers. There's a useful notion of receptive fields. This is which input will make a particular neuron have as high a value as possible. So if you look at the input neuron on the very top, it's tied to the upper left pixel. Its value is as high as possible when that pixel is white. So its receptive field shows a white pixel in the upper left corner, and then the checkerboard pattern shows it doesn't care. Those other pixels can be whatever they want, doesn't matter. It's going to maximize its value when the upper left pixel is white. So now we get to start building our neural network. If we want to build one neuron, and by the way, no relation necessarily to biological neurons, different topic. We take each of these values and we add them all up together. So in the case of this input, we add these up, we might get something like a 0.5. The trick is, though, we don't just add them straight. We weight each of these values. We multiply them by some number that's between -1 and 1. So if all of those weights are 1, it's a straight addition, but when they're not, that number can turn out to be something very different. So instead of a 0.5, we get a -1 point something, and it starts to look very different. This is, when people talk about neurons, this is most of the time what they're talking about is a weighted sum of whatever's going into it. You can think of it as a voting process. So each of these inputs get to vote on what the value is going to be coming out, and their vote might be weighted high or negative, the opposite of their vote, or not care at all if that weight is 0. We'll represent it visually with positive weights being white, negative weights being dark, and the width of the line being roughly proportional to the magnitude of that. Now, the one other thing we want to do with that weighted sum is squash it so it doesn't blow up numerically. We can have a lot of inputs that we're adding together. Those numbers can get big very fast. And so we squash that down. And the way we do that with the sigmoid squashing function is we might have an input. We throw it on the x-axis. We draw a vertical line up. Wherever it crosses the curve, we draw a horizontal line across. And that's our squashed version. So for small values, it's pretty close to no change. But as that weighted sum gets bigger, the squashed version will never be greater than 1. And similarly, no matter how negative it gets, the squashed version will never be less than -1. So it takes this infinite range, squashes it down to +1, -1, and then we're good to go. Our 1 point something becomes 0.7 something, and we have a neuron, this weighted sum and squash operation. Now we can take and do this again and again. We can make as many neurons as we want and connect them all to our inputs. The only difference between them is they have different sets of weights, different connections. To simplify our picture, we'll just assume they're either +1, -1, or 0. So they'll be white, black, or missing entirely. But in reality, they can be anywhere between plus and -1 on the weights. As we do this weighted sum, the receptive fields start to get more interesting. So you can see this first layer neuron on the top sums the input neurons from the upper left and lower left pixels. And now, not surprisingly, its receptive field, the input that makes its value as high as possible, is white pixels in the upper left and lower left position. Similarly with the other neurons there. Now what's fun about this is we've gone to great pains to make sure that our first layer values are between -1 and 1, just like our inputs. So they look exactly like the inputs, so we can turn around and use them as inputs to another layer and build it in exactly the same way. And we have this Lego brick effect where the one fits into the next perfectly, and we can make that Lego brick tower as long as we want. There are neural networks with tens or hundreds or even over 1,000 layers. You just keep doing this again and again. As we do this, each time the receptive fields get still more and more complex. And you might start to notice that some of these receptive fields start to look like the types of things that we're looking for. Solid images, vertical, horizontal images. Now, to throw in a kink, there's actually different types of neurons. So, and there's different types of squashing functions. So here's another squashing function we'll call a rectified linear unit that's really popular. And in this case, very simple. If the number coming in is negative, set it to 0. If it's positive, keep it. It's super fast to compute and has some really nice numerical properties. One of those things stumbled onto because it was convenient and it performed well, and so it's stuck around as a mainstay of deep neural networks. And with the combination of positive and negative weights, you can always take and invert your receptive field. If you look at the top there, the second layer neuron had a receptive field of all white pixels. Because we have a negative weight connecting it to the last layer neuron there, the second to top on the last layer, all of a sudden its receptive field is all black pixels. Its value will be the maximum when the input is all black. Now, we can do this as many times as we want. We're all done. We take a list of our answers that we want to get, all of the categories that we want to sort our inputs into, or all of the values that we want to be able to classify. And in this case, solid, vertical, diagonal, or horizontal images, and those become our output layer. Now we are ready to take an input, in this case, a horizontal image, and step it through this neural network and see whether our network classifies it correctly. And so we take our input, we propagate it to our input layer, we get the -1s on top, the +1s on the bottom, we do our weighted sums and propagate it to our first layer, and you'll see that some of those pixels cancel each other out. If you look at the very top neuron on the first layer, it's adding a +1 and a -1, so it's a 0. 0 is represented with gray there, so those top two neurons get grayed out. And each time we go, we see that some of these sums cancel each other out, some don't. By the time we get to the very end, there's only one neuron that doesn't have a value of 0, and it gets combined in our output layer, and it sums those up. And so our horizontal neuron in our output is the only one that's not 0. And so we know that's our answer. It has the largest value. And sure enough, the receptive field of the neuron that feeds into it matches our input exactly. So we could have guessed that that was going to get a good match. Now, this worked out really nicely because I cheated and put all the right weights in there to make this do exactly what I wanted it to do. In reality, when you start training a neural network, you don't know that you're going to have close to the right answer. And so in this case, the way you would start with that then is you get a neural network and you run your answer through, and you'll get a different answer than the right answer. So in this case, we know that the truth is a 1 for a horizontal and 0 for everything else. We know it's a horizontal image, but we might get an answer that's entirely different, and then we can take those differences and combine them in some way and get an error. This tells us just how wrong we are, which in turn tells us just how big a correction we need to make to get better. Now, making that correction, that is what we mean when we say learning. It's adapting to make that error go as small as possible. And the things we get to adapt are the weights. All of the weights that we saw connecting one layer to the next, they're all knobs. They're all adjustable. The trick is, that's a lot of knobs. And so knowing how to go through and adjust them all is tricky. So we use a trick called gradient descent. If you've ever tuned an analog radio, you can be off and get a lot of static, and you adjust the knob a little bit, and it clicks right in. and then you adjust it a little further and you get back into the static. Well, this is what happens with each of these weights. There's a sweet spot where that weight gets the error as low as possible, and that's what we want to find with each of them. So this ball represents the position, our position on our error axis in the y and the weight value in the x. As we adjust the weight side to side, back and forth, our error goes up and down, and we want to find the place at the bottom where it's the lowest. The trick is we don't know what this curve looks like automatically, so what we can do is just like with a radio, we turn the knob one direction. Does that sound better? Oh, no, that sounds much worse. Okay, let's turn it the other direction. When you're tuning a radio, that's easy to do. You get the feedback automatically. In a neural network, you adjust the weight, then you go back to the beginning and you run all of your multiplications and additions and squashings all over again, which is not so bad until you remember that you have to do that not just for one weight, but for all the weights. So every time you present it with a new input and you have to go back and adjust everything, you're running through this thing as many neurons as you have, which is not too bad with the network that we built, but imagine a network with tens of layers with thousands or millions of neurons per layer. And you can't do it. There's just not enough compute time, ever. Luckily, someone came up with a very clever idea, which was, well, let's not adjust the knob, let's just calculate what the slope is. And the clever part was knowing how to do that efficiently without having to recalculate your neural net. So this is getting pretty far down into the weeds. I'm going to talk about backpropagation. Feel free to tune out, but this is what makes neural networks work. It's rarely explained, but it's not that complex. I'll warn you, there is calculus, but you can ignore that too and still get the sense of what it does. The calculus comes in because we just want to know the slope of that curve, and that's a derivative. Quick review, slope is just if I change the weight in a little bit, how much does the error change? So change in error over change in weight. There's a lot of ways to represent that mathematically. We'll use the one on the bottom because it's technically the most accurate, but all it is a change in one thing for a small change in another thing. So anytime you see the little squiggly D's, just think slope. So to get it, you have to know the error function. When you know it, you can take the derivative, you can calculate that slope, then you know which direction to move to turn your knob without trying it first. The other thing that helps this work is chaining. Imagine you have a neural network that's many layers deep and you're adjusting a weight way in the back and you want to know how that's going to affect the error at the end. That's a very complicated function for how those things interact. Luckily, we can cheat. So with this really simple neural network here to illustrate, there's one input, one intermediate neuron, one output. It's a trivially simple thing. We can see with the weights in between that the intermediate value y is just the input x times the weight w1, and it's easy to take the derivative of that. Similarly, output e is just the weight, is the intermediate value y times the weight w2. And we can see in each of those cases, we see this, that's the slope. If I change one, how much does the thing on the end change? Now, because this is so trivial, we can write the whole thing. The output value is just the input value times both of those weights. And the slope, the change in the output for a change in that first weight is very easy to calculate. It's just x times w2. But note that this is just the product of these other two slopes that we already calculated. This is chaining. This is the trick. So if we have a neural network that's many layers deep, we want to know if I change some weight deep in the neural network, how much does the error change and in which direction? I just go to the end and I take one step back and I say, well, what's the slope? If I change z, how much does my error change? If I change y, how much does z change? And so forth, all the way back, and then we can just multiply those things together. So now we have something that only takes one pass through our neural network to do. And it's actually not too hard either. The individual pieces of a neural network are simple. We have multiplication of the weights, addition for the sums, the squashing, which is a little sneakier. But in the case of multiplication of weights, to get the slope from one to the other, we just write the expression, take the derivative, and, oh, it's easy. The slope from going from one to the other is just that weight. So that step in the chain, that link in the chain, trivial to compute. For the sums that we do, finding the slope, change in z for a given change in a, we just write the expression, take the derivative, and there's the slope. And this one's kind of intuitive. If I'm adding up a bunch of things, and I just change one of my inputs by 1, my output's going to change by 1 too. So this 1 for 1 is a slope of 1, which is what the math tells us. Okay, our sigmoid squashing function. So this is a little hairier. You can definitely take the derivative of this and calculate it. But if we represent it as this, sigmoid has a really nice property where the derivative is just the function value times 1 minus the function value, which means that calculating it is dead simple, very fast. We actually didn't even have to do any fancy college level differentiation, and that's easy too. Rectified linear units, trivial. If our value is is negative, our slope is 0. That's flat. And if our value is positive, again, the slope is 1. It's just a 1 for 1. So these are the individual links in the chain from which we build back propagation. Now with these simple computations, we can go through and we can start with a fresh neural network where all we choose is the number of layers, the number of neurons per layer, and random weights connecting them. So it's a completely noisy, definitely wrong, staticky network. And we start with a stack of images where we know for each image what the right answer is. This one is solid, this one's horizontal. A human has looked at them and definitively stated this is the truth for this image. Then we can take that image, run it through the network, compare the answer we get to the answer we know, use that error, back propagate, and tune all of those weights just a little bit in the right direction, and then do that over and over again. And if you do that with a few hundred or a few tens of thousands of images, then you'll take this giant neural network and you'll kind of bring it down, and all of these individual weights will settle down into their lowest possible error, and you'll get the best answers you can hope to get from this network. And it won't look this clean, but you'll get something that behaves nicely like what we started with. Now, the last little technical detour. When working with images, there is another trick that helps. When you talk about 5 megapixel or 15 megapixel images, that's a lot of input neurons. And that makes for very big, unmanageable neural networks. So when you want to deal efficiently with images, convolutional neural networks have proven them to be very useful. 9 times out of 10, when you hear about AI or deep learning or something big, some big tech company did something cool and extracted, koala voices from random forest noises, it's some variation of convolutional neural networks. There are some notable exceptions to that, but that's the state right now. So instead of a 2x2 image, we have an 8x8 image, and what we would like to do is determine whether an image is of an X or an O. So just 2 categories. We want to handle a robust variety of images, and the trick there is that to a computer, pixels are all plus and minus 1, so when it goes to compare, it sees a lot of disagreement. And it's not immediately obvious whether those things are the same or not. So one of the tricks that convolutional neural networks uses is to take little pieces of the image and match them to little patches little features and match them with little patches in the original image. And when doing that, you can start to see the similarities a little more clearly. So for instance, consider these features. A little diagonal line, upper left to lower right, lower left to upper right, and a little X. Now with these, we can actually go through and match pieces of an X quite well, and it doesn't matter if those pieces are rearranged a little bit. So if you'll forgive a little bit of arithmetic, actually determining how these things match, one way to do it is to go through, match the feature to a patch of the image, pixel by pixel, multiply the values, sum those up and take the average. So for instance, if I line up this feature in this location here, and I start one by one comparing the pixel. Well, pixel value of 1 times 1 equals 1. Great. I'll keep track of it over here in this like little history of comparisons. -1 times -1 equals 1. Great. And as I go through all of these, because they match perfectly, I get a value of 1. The average value is 1. And then on this copy of the image, I'll put a 1 right there to represent that in this location, this feature matched perfectly. If I try another location, you can see first pixel matches, second one matches, the third one doesn't match. And not all of the pixels match perfectly this time around, so we get some -1s in our answer. The average of that is somewhat less than 1. It's still positive, indicating a partial match, but it's less than perfect. So in this location, we put a different value to represent that partial match. So now imagine taking this feature and moving it all across your image and trying every possible match. That's convolution. And you get something that looks like this. And this image on the right, you can think of it as a filtered version of the original image. You can see what we would expect. This feature is a diagonal line, upper left to lower right, and it matches really well along that arm of the X, and then less well other places. We'll represent the convolution operator this way, and we can do this with all of the features that we have. And in each case, you see what you would expect. The X feature matches particularly well in the middle of the X, but not excellent anywhere else. And similarly, the other diagonal line matches well on the other arm of the X. These filtered versions of the images show where the features best match. Now the cool part here is these filtered versions look like an image. They also, each pixel is valued between -1 and 1, and we can turn around and treat them in turn like images. So if we represent in a neural network a convolution layer like this, we kind of maintain this cool property where the input looks like the output, which buys us our Lego brick stackability. Now, another important trick in convolutional neural networks' bag of tricks is pooling. And the way this works is you have a small window, typically 2 by 2 pixels, and within that window, you just look for the maximum value. Trivial computation. And then we'll record that and the step, again, typically 2 pixels, move it over, look for the maximum value, and just repeat this process through the whole image. And what you get looks a lot like the original image, just shrunk down. You can still see there's this nice match along the diagonal, a nice white line from upper left to lower right, but it's a lot smaller. It's only 4 by 4 pixels now, which means we've eliminated a lot of pixels but kind of compressed our information, our relevant information. The other thing that it's done is, if you'll notice in one of these windows here, it doesn't care where in there the maximum falls. So it means that your feature can match, it has a little bit of wiggle room positionally, which is how convolutional networks get some of their generality. It doesn't care exactly where things are. You know, even a Pablo Picasso face still looks like a face because the individual pieces are all present. So a pooling layer, again, a stack of images in, a stack of images out. And then normalization will look familiar. These are just rectified linear units, which we've already met. Everything negative becomes 0. And again, stack of images in, stack of images out. Now we can start stacking them together like Lego bricks, one after the other. And we can repeat this as many times as we want. And after doing this a lot of times, we get a stack of images. After we've done a bunch of pooling, they tend to be much smaller images. And then we can turn around and do what we did previously with our tiny images and do fully connected layers. Create an input layer, create an output layer. In this case, we just have 2 outcomes, the X and the O, and connect everything on the input to the output with weights, learn over the course of our training images which of our inputs are strongest predictors of the outputs. And then when we get a new input, just do the multiplication and the summation for each of these, and the one with the highest value wins the vote. And so we know this particular input was an X. So this is the magic. Represented a fully connected layer like this, as we mentioned before. Inputs look like outputs. We can stack them together. I have not told you how to do backpropagation for convolution and pooling, but there are similarly straightforward ways to do that. So we can backpropagate our error all the way through this network, learn all of those weights, and interestingly with this, what you also learn is the pixel values in your features. So those nice X's and, the diagonal lines and the X that I showed you that helped us recognize an X, in an actual neural network, you wouldn't know those to start with. You'd start with random features. And you would adjust each of those pixel values up and down also with all of your weights. And they would settle in on the features that best help predict. This is why popular press can be forgiven for talking about convolutional neural networks as magical. Because they are not magic, but they're pretty damn cool. So what that gets us now, imagine we take yet another step back. We're at 64 pixel by 64 pixel images, just another factor of 8. So we take a satellite image and chop it up into lots of little 64 by 64 pixel chunks, and we just step across that image. Every single one, is this a house? Not a house. House? Not a house. All the way through. Not a house is black. Yes, a house is white. And when we're done kind of chopping up this image and stepping all the way through it, we get an image like the one on the right. So this is my goal here is to pull back the curtain, on the Wizard of Oz, and to show that like this stuff, yes, it's powerful, yes, it's cool, but it's not magic. It's something that anyone here could code up, given enough stubbornness. When you buy a magical black hardware box that can do these calculations very, very quickly, this is all that's going on under the hood. It's hardware specifically designed to do these very calculations really, really fast. Now, this little village in Mozambique is just a small piece of a bigger countryside, which in turn is just a small piece of a much larger country, which is, again, a small piece of a much larger place. So the power comes to be able now to take what was just numbers and pixels and get information now that can be turned into action that can do something like taking internet to the world. Thank you very much for listening. I'll be happy to take any questions you have. Let's see, hand right here.
Can you talk about the difference between, or the advantages of having a fully connected network versus partially connected? Because in your original examples, not every input node was connected to all of the neurons, but in others it was. So do you make those decisions, or do you rely on the weights to sort of zero themselves out?
So the question is, what's the advantage of a fully connected network versus a partially connected one? So the diagrams I showed earlier on only showed some of the connections. The others were actually present, but were zero or assumed to be close to zero. So those were actually intended to be fully connected networks. The only downside of having everything connected is it's just more computation. But the upside of having everything connected is that the computation looks like multiplying two-dimensional arrays of things together, which computer hardware is very, very good at. So, yes, right here.
How do you differentiate pictures, home and shiny objects like small lakes? How do you differentiate?
So the question is, when you're looking at an image, how do you differentiate between a home and a shiny object, like a small lake? If it's something that a human can differentiate, then the idea is we can train the machine to do it. In the data that you train the machine on, presumably you have lots of pictures of homes that a human has said this is a home, and you have lots of pictures of things that are not homes, including, hopefully, like a small shiny lake. And so it can learn, they might have some things in common, but it can then learn the differentiators between them. What you hit on is a really important thing when working with real data, which is to make sure that your training set is rich enough so you don't accidentally misclassify things just because you've never seen it before and it kind of looks like what you're looking for. So, yes, right here. Yeah, so the question is, when is it worthwhile to use a pre-trained model and when is it important to build from scratch? If you remember back to where I showed the receptive fields in this neural network, what happens in deep neural networks, especially convolutional neural networks, is you get this really rich and interesting collection of receptive fields as you go, and then whatever you're learning to classify in the end, it feeds into that, and they vote on it. As long as you're classifying something that's interesting and that's easy to tell the difference, for instance, not just like a bright image and a dark image, like that's kind of trivial. If you're classifying something interesting, the neural network has to learn a rich set of intermediate neurons. And what that means is that if you want to learn something else on a pre-trained network, you can just substitute out the last layer. You can say, I'm not trying to do house, not a house anymore. I'm trying to do forest and desert. But the features that it's already learned, you just have to relearn that last step, which is a lot cheaper, a lot easier to do. And this is actually a trick that a lot of people use called transfer learning in the neural network sense, where you have data that's abundant, that's labeled, and so you can train your neural network on that. And then you have another data set where you're really scraping by to get just enough data points. And so you freeze everything up until that last layer, and then you just retrain on your own smaller data set. So, great question. Let's see, to get some spatial diversity, we'll go here and then to the back of the room next. So the question is, going through and chopping those large images into 64 by 64 pixel chunks seems inefficient since the vast majority of them are non-house chunks. Isn't there a way to eliminate a lot of that and speed it up? That's a super good question. The answer is almost certainly yes, but not that I have tried. I do want to use this opportunity to note this is not work that I personally have done, and I want to give credit to the team that has done this house finding work. A lot of really sharp folks at Facebook. I feel lucky to be able to talk about it, but I can't take credit for the insights that have gone into it. Yeah, right back there. So how does one size the neural network? Choose the number of layers, choose the number of neurons per layer. The comment was, it seems like a black art. I would say that it is a black art. Those are called the hyperparameters. There's like the parameters that control your parameters. The space, all the different possible combinations of neural networks you could build is so big that there's no way we can try them all. And so we've only tried, if you think of it as a vast wilderness, we've only explored a tiny region of it. And my understanding of the way that this has gone is some very dedicated and enterprising grad student says, I think this might work, or this is way too slow, I'm going to try this shortcut to speed it up. And then she finds out that sure enough, it's like the results are only fractionally worse, but it's 100 times faster, and then pretty soon everyone else tries that too. Now, we don't have a principled set of criteria for choosing these right now, So it could be that there are places in this wilderness where things are beautiful and perfect and slick and absolutely efficient that we have yet to discover. Let's see. Yes, right here. So the question is, have we tried evolutionary computation for developing the structure? Which, as I would suppose, would mean you have your set of hyperparameters, number of neurons per layer, number of layers, and then you have a set of these, you train them all, and then the ones that do the best, you make more that are similar to those and train those, and you do this over and over again. Unfortunately, the amount of computation involved in training one of these is considerable. It's not something I believe yet that we can scale to do a set of 10,000 of these and then reselect and do it again. So it's a great idea, but it will require another enterprising grad student to have some insights to help that happen. So yes, in the back.
Yeah, so what separates, sort of an extension of the question, but what separates, what do you do to improve the result? I mean, sort of in theory, you throw a lot of data at it and you get some results. Now, what do you do next, I mean, to make it better? And also, do you have to do any pre-processing if it's not one from zero?
Yes, so the question is, well, what do? You get one of these and you run it, and the results aren't quite as good as you would hope. What do you do to improve it? In practice, the biggest weakness every single time is in the training data set. As expensive as it is to compute, it's even more expensive to go out and gather relevant data and forget about having a human, much less a human that you trust, sit down and classify this carefully. If you have a data set like that, I think somebody said yesterday, and I heartily agree, like the value is in a really good data set. The algorithms and the computation, they're important, but they're easier to replace. They're easier to make up for. Yes?
How big of a training set did you use to do the analysis? How did you acquire it?
That's a good question. That is work that I personally didn't do that I don't know the number off the top of my head. So, sorry about that. Yeah, it's right there. Sorry, can I get you to repeat it just a little bit louder? It's just a large room. So the question is, why convolutional neural networks instead of a fully connected neural network all the way through? That's a good question, and it falls into this realm of questions of the vast. There's just a lot of things that haven't been tried, and it's expensive enough to try them that there's just sorry. So the question, as I heard it, was why not do another scheme where you have this answer feedback in a different way? I'm sorry if I'm fuzzy on the details, but to be able to more efficiently train your network. There's a lot of room for exploration here, a lot of room for researchers to try new things, and I don't know how that would work. So it's a good question. So yes, on the floor.
You have changing demographics, so it's constantly changing. Do we have anything so that you don't have to retrain every time?
So the question is, there's changing demographics. Is there anything we can do so we don't have to change the model every time? So you're talking about if let's say I trained a model on a bunch of customers, and then 2 years later, those customers were 2 years older. Is there some way to generalize? This is a fundamental limitation of statistical machine learning. It assumes that the world will look the way it has always looked. And if you can solve that problem, there'll be a lot of people who'll be interested to hear about it. Yes, way in the back.
Yeah, regarding transfer learning, is there any like special consideration that has to go into the data set and the network that you're building off originally? Like, does the original data set have to resemble the type of data that you're working with currently?
So the question is, if you're doing transfer learning, is there anything you have to do to make sure that it'll transfer well, like making sure you're learning a similar type of problem, like the data looks similar? And I believe the answer to that is yes. My personal experience there is very limited. And I think because of the cost of training networks, most people's personal experience is very limited. We are still awaiting some kind of a general principled framework in which to formalize the answer to that question. So, yes?
So you did a great job introducing what's called them the building blocks of the system. Could you talk a little bit about how you iterate over them, determining how many more to add, subtract, adjust the hyperparameters, and how long that process typically would take someone to develop?
So the question is, how do you adjust your hyperparameters and what's the process of improving that overall structure? This is the same metaphor of exploring in the wilderness. We just have a small area that we've explored, and so you can read other papers, talk to colleagues, and to see things that they've tried and have not worked for them. And at that point, it's a trial and error, adjust based on your gut and based on, what somebody said, someone else said they did. Like, it's really still pretty Wild West. How long do you keep monkeying around with that until you get until your paper gets accepted? So, yes? So question is, when you're doing the gradient, show the little marble running down into the bottom of the valley, you can actually imagine a little more complicated valley where it gets stuck on a ledge and actually can't easily get to the bottom. That's called a local minimum as opposed to the global minimum, which is like the lowest it could possibly get. And one of the pitfalls of gradient descent literally means going down the hill is that you stop when you get to the bottom. I don't know of, so in general, mathematically, that's like a capital H hard problem. For neural networks, I don't know of any trick there, although because there are so many weights, it is my strong suspicion that this space that you're rolling around in has so many different directions. Even if you get caught in a shelf this way, you can kind of roll off to the side. There's always adjusting another weight that gets you a path down. And there's actually, you may never get to the very lowest point, but there's lots of points that are all kind of close. And so you just have to kind of find one of them. So right in the front row.
Follow-up question, if you rerun with different initial weights, do you get essentially the same network at the end?
So the question is, if you rerun with another set of random initial weights, do you get the same set of weights at the end? I don't know, I've never tried it. It's one of these things where it costs so much to do. Mostly people stop when they get one that works. But my guess, because the number of weights is so large compared to the number of outputs and the number of inputs, is that you'd get a different set. It'd probably behave similarly, but the weights themselves would look different. All right, I apologize, but I am going to have to bail. I will be around. There is a Facebook table, which I'll be at until lunchtime, and I invite you to come by and hang out. Thanks very much for your attention and your questions.